everyone. This video is to provide you an explanation of the AI-SPRINT Runtime tool named POPNAS, which is the automatic deep learning component within the AI-SPRINT project. It is a support for application developers and AI experts, and it is a neural architecture search technique in the runtime environment. The idea is the following. By default, an AI expert or an application developer, in order to produce the deep learning or machine learning model, have to process data, to develop models, improve models in order to maximize their accuracy, and implement them inside modules and applications. Typically, this set of models come from good intuitions and a lot of human effort, but we know that not always good intuitions, especially in deep learning field, lead to good architectures, and many times the human effort is very, very too much and expensive. For these reasons, there are many solutions, for instance, the Google Cloud AutoML, but there are many issues related to this kind of third-party applications. For instance, the code is not open, nor the models, and sometimes it may be very, very costly. For this reason, we have the Pareto Optimal Progressive Neural Architecture Search, which is the AI-SPRINT Neural Architecture Search proposal. And it is based on the Google solution, which is named POPNAS, which is Progressive Neural Architecture Search. But the idea is to make this tool even faster by keeping the same accuracy of the original model. So we are flavoring architectures with minor training time under the same accuracy, thanks to the Pareto optimality training. So the idea is the following, and the improvements we achieved are based on time predictors, which are machine learning models that are able to estimate the time performance of the networks to search. And according to the accuracy predictor, which instead predict the performance of these models, the two architectures are able to create a Pareto front from which sampling the optimal architectures with respect to accuracy and also time, as you can see in the figure. So the idea is the following. Without the neural architecture search in AI-SPRINT, users, or in this case AI developers or general developers, have to manually define deep neural network models, the training and the architectures themselves have possible stuck in local minima, and sometimes this process is prone to bad intuitions and very time consuming. With POPNAS, we have the automatic architecture search. It is very performant, and we have custom state-of-the-art like models after the procedure. It is a very good trade-off between time and evaluation metric, and this requires no human effort in terms of experts. So this is a demo which will show you how to use our POPNAS tool.
In this video, I will provide a short introduction on how to use the POPNAS V2 web interface to execute a neural architecture search experiment on a remote server. On the home page, you can have a brief introduction on the pages provided by the web application and a short introduction on how POPNAS V2 works. If you want more details, you can refer to the article, which URL is provided on the bottom of the page, or to the project documentation. First of all, you need to upload a valid dataset. On the right, you can see the list of datasets present on the server. For example, we have a single dataset called the Euroset. To upload a new one, you use the form on the left. You provide the name. For example, brain tumors is a medical dataset. and we provide the zip file of the dots, which must have a specific structure to be read from the POPNAS tool. In particular, it must have a specific folder for each split, which is prefixed by chars, and then followed by the name of the split. The training one is mandatory, while the validation and tests are optional. And each folder must contain a folder for each label, and inside the folder all the samples. Wait a bit to complete the uploading of the dataset, and you should see it listed on the right after the upload is complete. Set to start a new run, you can use the other form, and also here you need to select a name. Okay, the dataset has been uploaded successfully. You select a name for the run, so for example, brain tumors run. You select the dataset from the drop-down, and then you need to provide a configuration file. Configuration is quite complex, but you can get the template from the button. Here we're going to download. Okay, and the default parameters are already suited for a general application. You just need to configure the resize option, since all images must have the same shape, and so you need to provide a way to reshape these images. You can use if all your images are of the same size, you can simply use the size of the images, otherwise you can downsample them to a suitable resolution. Okay, so we save the file, and then we upload the configuration and submit the run. Okay, the run is started. You can check the run executed and in progress in the relative page. Here you can see there is a run that is already complete and the new run that we are currently executing. Clicking on it, it will reveal some details about the run. For example, the configuration we have provided, that the status, which is running, the action we can perform on the run. For example, you can stop it and resume it later to free the resources. And when it's complete, you can also download the best models for the output of the run. Actually, since this run is in progress, you can have a better overview of the visualization tools on the completed run. In the training tab, you can have an overview of all the training results of the networks by running the TensorBoard, and you can select each run to see how the accuracy, the F1 score, and for example the loss change with time, and also compare multiple architectures. In the results tab, instead, you have an overview, a tabular overview of all the results of these networks, and you can also sort them, for example by accuracy, and set some filters. For example, max execution time of 600 seconds and minimum accuracy of 0.9. Here we go. Instead, in the plots tab, you have an overview of all the plots produced by the algorithm, which can provide some valuable insights on how the run performed and which operator and inputs are better. For example, here are some metrics used with predictors, the overview of the accuracy predictor, the inputs used in U equal to Q step, B equal to T steps, and so on. In the help page, instead, you have more information about how to upload a valid dataset and how to configure the POPNAS V2 run, which is actually quite complex, but there is a very exhaustive guide for each parameter inserted in the JSON configuration, and also a small overview on how the output folder is structured.
This is the set of experimental results coming from the paper of POPNAS, which has been published on an international journal. And we can see that with respect to the reference algorithm, we reach the same performance in terms of accuracy with a search speed which is 4 times higher. So it allows to preserve a lot of resources in this sense. And with regard to the best architecture identified after a longer training of the best selected one, we see that we achieve the same performance of the reference algorithm, and the training time is 2.5 times faster with respect to the POPNAS algorithm. So this concludes the presentation. Here you have the references with the 3 versions of the POPNAS algorithm, and you can check more results and more details inside these papers. And here is also the GitLab link to POPNAS. So thank you very much for your attention.